Rightio, g'day students, welcome to today's lesson. We're looking at our first lesson in Unit 4, Topic 2 today, which is exciting. Now we've got a lesson on reaction pathways. We're particularly looking at retrosynthetic pathways, where we look at getting complex molecules and break them up into simpler molecules. And we also think about how do we use that efficiently to make our target molecules. So the first goal of today is that we want you to appreciate that chemical synthesis involves the selection of particular reagents to form a product with specific properties. So let's have a look at some retrosynthetic pathways and what that is. So we've got this target compound in mind. So once the desired compound have been identified, it's up to the job of a chemist to design efficient reaction pathways to convert readily available materials to more complex ones. Now, the retrosynthetic pathways, its idea is as they're alternate pathways to synthesize products, so chemists will start planning from the target and work backwards to the simpler molecules. So they're going to be looking at the precursors to the more complex molecule. So it's important to note, though, that no reaction gives 100% yield. So it's useful to break the complex molecules up into precursor molecules and then recombine them. So that's convergent synthesis to reduce the number of steps in the pathway. Now, it's also important to minimize waste. It just makes good efficiency, doesn't it? Use greener solvents, so there's less harm to the environment, and to conserve energy and to conserve resources. Now, if we have a look here, there's two pathways to making ibuprofen from 2-methylpropylbenzene. You can see what we've got here. On the left-hand side, we've got a green pathway. You can see that we've got 1, 2, 3 steps. Involved in those steps as well, we've got hydrogen fluoride. And then we've got hydrogenation, and then we've got palladium and carbon monoxide. So we've got 3 steps, and we've got less deadly stuff, have we? Let's have a look at our other catalyst that's involved in the brown pathway. So you can see that in the green pathway there are fewer reactants, and therefore a higher proportion of the atoms in the reactants are present in the final product. Therefore there's going to be less wastage in the final product. Now, if we want to just think about this idea of linear versus convergent synthesis. So linear is just getting all the simple molecules and putting them together until we get the overall yield. So linear synthesis is a chemical synthesis process in which a series of linear transformation reactions are used to convert a reactant or some reactants into a product or multiple products. Now that's got pretty low efficiency. So remember, no reaction is 100%. So the process is going to be pretty long, and the overall yield is going to be pretty low. Now, convergent synthesis is a chemical synthesis, remember, in which pieces of the desired products are made by a set of reactions, and the pieces are combined with each other or via a set of reactions. Now, it's got much higher efficiency, and the process is shorter, and the yield is better than the linear model. Let's just think about this precursor as well. So if we have a complex molecule and we can break it up into 2 precursor molecules, we're going to use this double arrow. So we've got a double line like an equal sign and just an arrow on the side there. So if we have a look at methylpropanoate, so remember that to make methylpropanoate, that's an ester, so you've got to combine an alcohol with a carboxylic acid. So in this case, if we're going to make methylpropanoate, we need methanol and then propanoic acid, and that's where that would be there, joining. And we'd just note then that the precursors to methylpropanoate would be propanoic acid and methanol. And you can see that I've just used that arrow there. reaction pathways is just a series of one or more steps or reactions that can be used to convert a reactant containing certain functional groups to a desired product with a different functional groups. So if we have a look here, we've got alkanes and alkenes. Oh, we did that already. Okay, so we've got an ethane and an ethene here, and you can get the same idea if it's propane or propene or methane or methane. It's well, we wouldn't get methane, but you get the idea. So we've got ethane, and we can do that. Now we can go ethane to a halo ethane by just adding in chlorine under UV light, and then we can hit it with a bunch of sodium hydroxide to turn it into ethanol. And then we can turn ethanol into ethanoic acid by acidified dichromate solution. And we can mix ethanoic acid with an alcohol, and it's got to be an acidified alcohol to make our, what's this one? That's got to be the alcohol bit there, and that's got to be the carboxylic acid, so that's got to be an ester, hasn't it? So and this one's an alkyl ethanoate, so if that's just a methyl group, that's going to be a methyl ethanoate, for example. Now we can also do the pathway from ethene. So let's have a look at this right hand part now. So consider how to form ethyl propanoate using only an alkane or alkenes. So we've got two different pathways to make ethanol. We want to get ethanol. Remember, that's the ethyl part of the ester. So how do we make the ethanol? So this is what we've got to end up at. Do we just go that way or do we go that way? So we've got this idea. Well, there's only one step there, so that's probably a good idea. Or there's a two-step there as well. So that makes life a little bit interesting. So that's two steps there. We can also make propanoic acid. Now we want to start with what? Propane. So just pretend that that's a prop and that's a prop there, or propene. So we can use a propene precursor or a propane precursor. And is it going to be easier to do that step or those two steps? So we've got 1, 2, 3 there, or just 1, 2 steps there. So we'll have to think, well, what's the most easiest way? So, and then we'll just mix the, what was it, propanoic acid plus the ethanol to make ethyl propanoate. So we want to just consider, how do we make the ethanol first of all when we are going to start to form ethyl propanoate? So we've got two different pathways that we can have a look at. So the first pathway is just mixing what? Ethene with hydrochloric acid to form chloroethane. So that's our intermediate product. And then you can just add hydroxide to that to get chloroethane. And that will form ethanol. So that's a two-step process. And the intermediate is chloroethane. We can also note that the inorganic products are just placed above the arrow. The second pathway is just a one-step, and it's addition reaction with water. We've got a phosphoric acid catalyst. And so in this case, the best option would be the most direct. So remember percentage yield, that's important to note. One step will give you a better yield than a two-step process. If we have a look at making propanoic acid, and we've got two different ways. We can do a single-step addition with reaction with water, or we can do an intermediate product using chloroethane. Well, it'd actually be chloropropane, actually, wouldn't it? So in this case, due to Markovnikov's rule, just remember that the rich get richer. What's that? The carbon with the most hydrogen likes to get the most hydrogen. So that's going to lead to the formation of 2-chloropropane, which is not going to be useful in forming that propanoic acid. So in this case, you're going to have to go to pathway 2. So we're going to be using this one up here. rather than the single-step addition reaction with water because of Markovnikov's rule. So the inorganic reactants, remember, are placed above the reaction. In this case, the best option is not the most direct. So here we have just a reaction pathway for the preparation of ethyl propanoate. You can see that the top line there has got the structural formulas. We've got that single-step addition reaction with water from ethene to ethanol. And then we've got the multi-step one down below for the formation of propanoic acid from propane, using chlorine gas to form 1-chloropropane, then hitting it with a bunch of sodium hydroxide to form propane-1-ol, and then hitting that propane-1-ol with acidified dichromate to make propanoic acid. Now you just mix that alcohol, the ethanol, with the propanoic acid in sulfuric acid to form the ester ethyl propanoate. Now look, there's going to be a bunch of considerations when you also have to devise a synthesis in industry. You're going to have to, of course, think about the overall yield. So think, well, convergent and less steps is going to give you more yield. Think about the cost factors. Think about the reaction rate, and then also the equilibrium position. Does it favour products or reactants? I think about scaling up to the industrial scale, the green chemistry principles of using environmentally friendly solvents and so on. Think about those byproducts, and this is particularly interesting with looking at the chirality of the products. So remember, that has to do with that central asymmetrical carbon. So if we have a look at these mirror image isomers called enantiomers, I never get that right, we've got to think about which ones are desired, and thalidomide is a classic example. It was a pill developed back in the 1950s, and it was given to pregnant women to help them with morning sickness. Now, you don't want to get morning sickness anytime soon, kids, and it's only girls, that's for you. It just makes you really sick when you're having babies and when you're pregnant. So you get the vomits, etc., or just feel nauseous. Yeah, anyway. So thalidomide was a medicine for morning sickness and had two different isomers. The S form of isomers actually led to birth defects and given to pregnant women. So it was quite dangerous. The right-hand side, or the R thalidomide, was the one that actually perhaps had the good stuff, but the S form was dangerous. Now, not all isomers are dangerous. Some might just be wasted. So you might be making up a precious medicine with the wrong isomer, and it might just be excreted out of your body. So you have to consider that. So having a look here on the right-hand side, we've just got a little bit of a flow chart when considering some of the steps in devising a chemical synthesis. So first of all, just think about the structure of the required compound or target molecule, and study that and identify the functional groups. Then a synthetic pathway is devised using the knowledge of the reaction of functional groups. As a synthesis may require preparation of a number of intermediate compounds. Now, the formation of isomers and other byproducts need to be considered as well. For example, the substitution of reaction of propane with chlorine produces a mix of isomers such as 1-chloropropane and 2-chloropropane. So remember, that's what Markovnikov's rule. Now, it's going to favour the one that you don't want generally. Now, more than one possible pathway may need to be considered. So remember our example with ibuprofen as well. We've got the brown and the green pathways. So more than one possible pathway may need to be considered, as a desired product may be synthesized by a number of routes. Now, the methods of separation of desired intermediate and final product form, isomers and other byproducts should also be considered. Consider the final product in terms of purity and evaluate that purity. And finally, consider the yield, as not all of the reactants are necessarily converted into product, and That's important to remember with that equilibrium position. Rightio, we've done a bit today, but are you able to appreciate that chemical synthesis involves the selection of particular reagents to form a product with specific properties? When you're good at that, please have a crack at the mastery questions.